Okay, and so no more delay. Dr. Burk, we turn it over to you.
All right. Well, hope you guys are having a pretty good day here. So what I want to talk about today is a topic known as tessellations, tiling, and you do see this in the real world. I mean, here's some tiles right here. And tiling, it could be a little bit of hard work, I guess, mathematically and also physically. It can definitely be rewarding, physically and also mathematically when you start digging into it.
You started the recording.
I sure did.
Okay, no problem. I just want to double check.
We'll just put it up there for verification purposes.
Thank you. Sorry to interrupt.
So right here, this is actually a picture I took a few years back. I think it was in Oklahoma. And I was like, wow, look at that tile floor. That looks awesome. Now, we see patterns everywhere in life. We see patterns. Look, Cheez-Its. Cheez-Its, if you haven't gotten some yet. You definitely can get a pattern structure right there. Your molecules, corn. There's a nice little pattern to it. It's a little corny, I guess. There's my corny joke. Stuff with honey. The cells in your body, there's a nice little pattern there. Even out in the desert, molecular level in, in our animals. So we see patterns everywhere we look. And it makes you kind of wonder if there's some kind of message out there that someone's trying to tell us. And one of the passages that I really like is over here from Psalms. It says, the heavens declare the glory of God. The skies proclaim the works of his hands, and day after day they pour forth speech, and night after night they display knowledge. So the deeper we look into the science and the deeper we look at the mathematics, the more we actually see the fingerprints of God. And that's one of the reasons why we really want to study the science. The deeper we go, the deeper we can actually see the evidence of a creator. Okay, now, when we're talking about tiling is a process in which I'm going to get some shapes and I'm just going to line them up in a way so that we're not going to have any overlaps. So there's going to be no gaps right here in my tilings. And when we were tiling a floor, you definitely don't want to have any overlaps, but that's why they make saws, just in case something like that happens. So for the tile floor, when you look at it, it makes you start wondering, at least the mathematicians just start wondering, I wonder if there's some kind of mathematical property here that we can exploit. Okay, it'd be kind of awesome if we can figure this out. Now, what we're going to talk about is a certain type of tiling known as, we're taking a rectangle and we're going to square this. And okay, so just kind of give you a little quick history here. This was a problem that was proposed in the early 1900s, and a lot of the problems that were proposed were in these books, just some kind of mathematical gem, where they sent out in these books some problems. This is the problem, I think, Canterbury puzzles and other curious problems. And it was kind of written in a kind of a rhyme kind of fashion to try to keep, I guess, people's attention or whatnot. But this is one of the first occurrences in which we're going to take a rectangle and essentially we're just going to line it with a bunch of square tiles. And it was asked, could you do this or not? And sometimes in these articles, if you could find a solution, you would mail it in, and you might win a little cash prize on the side. But in 1925, we had this perfect squaring of the rectangle, which was finally found, and it had 21 squares in it. And it took a while to get there. As you see, you get, I guess, 23 years, which is a great prime number, by the way. A lot of different reasons behind that. But this is just looking at a rectangle. So the question is, what about squaring the square? And that took some time also to kind of discover. In fact, it was conjectured in 1930 that it was not even possible. So you work a problem for as long as you possibly can. You can't find a solution. I guess there must not be a solution. And that's typically what you do when you're writing up proofs. If you can't find it, maybe there's a counterexample. So people started searching for counterexamples. But eventually, it was discovered that you could find a perfect square, or square the square, in 39. Now, this right here was just kind of stumbled upon, and it wasn't into later on where some students, in fact, the students were undergraduate students who discovered that you can actually square the square. And the individuals out in Cambridge, Burk, Smith, Stone, and or you say right there, and they developed a theory behind this. And interesting history of how to go about this problem. Now, what that goes to say is this: just because you guys are an undergrad, it doesn't mean you can't find something new. There's lots of stories in which undergraduate students were able to solve a problem that a professor wasn't able to solve. One story that comes to mind, a student, maybe it's undergrad, graduate, can't remember here at the moment, but he arrived late to the class and he's just scribbling down the notes that the professor had on the board, and he wrote down 5 different problems. And the student went away after the lecture, came back a week later, he says, I'm working on these problems and I still can't solve them all. I solved the first 2, but I can't get the next 3. He goes, what? You solved the first 2? Those were unsolved problems. You weren't able to solve them. I was just throwing them up on the board. And I guess that shows that it pays to be a little late to class sometimes. You don't get all the details. So you actually work through the problem. So things like that can definitely happen. So challenge yourself. There's a lot out there. Okay, so in 1940, they were able to find a perfect squared square. So when we're talking about these perfect squared squares, we make a little bit of distinction here. It's definitely possible to take a rectangle and you could square it. You just basically get 2 squares and put them together. There's a rectangle and it's been squared. Okay. But really what we're looking at are these imperfect squared rectangles. And this is where all the rectangles are going to have a different size to it. Now, one of them that you can almost do is this one right here. And this one incorporates the Fibonacci spiral to this. If you see me in class, you've probably seen this before, where you have 2 squares of the same size, so 1 and 1. And then you put a square next to it, 2 by 2. Up top you put a square that's size 3 by 3. And then what's the next Fibonacci number? 5. What goes on top? 8. And then so on and so forth. And you can see the Fibonacci spiral right there. Okay. So we definitely have an imperfect squared rectangle. And again, how can I find a perfect squared or imperfect squared rectangle? So that's kind of the question here at the moment. Okay. So how can we find the configuration that will allow us to construct a perfect squared rectangle? Okay. I want you guys to kind of think about maybe what you can do there. Okay. Okay, we're going to explore this. Now, before I get to that, I want to talk about something real quick about these tilings again. So with tilings, we're talking about no gaps and no overlaps. So if I'm talking about tilings, it might be a good idea to get a little bit better understanding as to what's really happening. And when I'm tiling, maybe like a M by M rectangle, and I want to tile it with A by B rectangles. You know, rectangles, squares is a square rectangle. So we're trying to understand the theory here. So whenever I start laying them out, there's certain configurations I want to do and certain configurations I'm really prohibited from doing. Okay, so just for sake of argument, suppose if I have a 6 by 7, I want to tile it with 3 by 4 little small rectangles. Is that even possible? Well, I can maybe line it up, take the 3 by 4, and split it in half. That would get me a 3 by 3 little block here at the end. Then I'm not going to be able to do so. I'm a little bit over. And if I try to line it up this way, I go up 4. That's going to leave me a little gap right there of 2, and I still can't put my tile in there. So I'm still having a little bit of a problem. Now, the question is, why? You know, the scientists would take that question and go deeper as opposed to saying, I can't do it. Why can't I do this? Well, part of the thing is when you look at it, we note that the areas, for one, have to all be contained within the area of the bigger one. you can see this real easy maybe with a checkerboard. You look at all the areas for the brown pieces, the black pieces, and I guess the lighter brown or the white pieces here, squares. And even if I was going to take this and extend it out a little bit to a 6 by 10, the question is, can I do this? So when I look at the area here, I do have 42 and I do have 12. And 12 does divide 42, but it's still not going in it quite well. Okay, and if I go up to 60, I can definitely see it's just not going to work. So when I'm tiling, I have to kind of follow these kind of ideas. This is really what's happening. So the area of the tiles must evenly divide the areas of the rectangle. The tiles must be aligned within the rectangle so that they cover vertically, horizontally boundaries of the rectangle. The dimensions of the tiles must be obtained to fully partition the dimensions of the rectangle. Whew, that's a lot. Okay, so math is saying this. The areas must divide. And not only that, when you look at the dimensions, it must be some kind of linear combination. Linear combination. Okay, so either M or N must divide A, or M and N must divide B. And that starts making sense. If I back up a little bit and I look at my my 6 by 7 and 3 by 4, I can see that neither 3 nor 4 is going to divide 7, so I automatically know that this is not going to tile. It's just not going to work out. Okay. So, once again, Fibonacci sequence, I can definitely go about from this vantage point, get my imperfect squared rectangle, but how do I still find these? So what I can do to try to find a perfect square rectangle is imagine if I actually did have a rectangle for the moment. And I know that I got to put squares inside of here. So what I can do is just maybe start trying to dissect it, try to partition it, try to start slicing it. So let's just take a rectangle, and if I'm making a perfect squaring, or have these perfect squares of the same size, once again, I can do that pretty easily, something like that. So I kind of want to avoid the situation. So I don't, when I'm squaring this, I don't want to put a square at the very top, because what's that going to necessitate? It's going to have to go all the way down if it's going to be contained within this, and that's going to force another square of the same dimensions to be inside of it. So what I want to do then is not partition it all the way, but partition it part of the way. So there's going to be my first square. Now, it looks like a rectangle, but hey, I'm just really bad at drawing. It's really a square here. Okay. Now, the next thing is, if I put a partition here, that's going to force me to have a square here and a square here of the same size. And I'm trying to avoid this scenario. Okay. So I'll just make another partition right here. And then I'll make another partition, and I'll keep slicing and dicing this. Just keep doing more and more partitions, more and more slices. Now, just kind of just on a side note real fast, a little, I guess a tangent, but tangent is still a math topic. There's actually a book out there, and it talks about the mathematics of cutting cakes. Could you actually believe that a mathematician went as far as cutting cakes? Why not cut pie instead? I don't understand that. But it's actually, I think it's by William Webb, and he's up in Washington State University, and he wrote a little book on, and it has applications in due to like maybe inheritance. If you were to have two siblings, who's going to get the fair share? Or if you were to have three siblings, what's going to be the fair share? Cutting the cake, cutting the inheritance. So there are some economical reasons as to why you want to look at that. But anyways, back to the main show. So what I'm going to do, I know this is going to be a square, so I'll just go ahead and label this. I'll say it has a dimension of D1 by D1 and D2 by D2. Now, if this has a dimension of D1 and then D2, what's the dimension right there? D1 plus D2. It's kind of like if I go back to that Fibonacci spiral, 1, 1, put a square next to it, has a dimension of 2, and I put a dimension on top, it's going to be 3, because I'm going to have 2 and 1 gives me 3. Okay. So I'll have D1 and D2 here. And if I go up here, what's that dimension? It's D1 plus whatever this is. So that's going to be D1 plus 2D2. And what I can do, I can keep working my way all around, down here, over here, and up here, where I take the dimensions, I add them up, and I get my dimensions down here. And once again, I'm just really bad at drawing. These really are squares. They look like rectangles. Now, since this is a rectangle, there's a few things we can actually glean from this. This dimension on top is the same as the dimension down there. Okay, do you guys see that? Also, the dimension right here is the same as the dimension right there. Why would that be important? Because it allows me to get an equation now. See, I know that this, and we said, is exactly the same as that, and I say the word is, I'm talking about an equation. So I can pull them all together. So now I have one equation. I can talk about it. Independent and dependent variables. I can solve for D1. It's going to give me my value of D2. So based upon what I make for D2, it's going to affect how I do D1. So I can come over here. I can look at my configuration. I can drop everything in. So D1 is going to be D2 all the way around. And if I form it again, D1 and D2 are the same. So had a nice try, but it didn't work out. Okay. So that means we go home, we give up. No, that's not what we mean at all. Once again, the scientists would say, well, why didn't it work? Not that, shucks, it didn't work. What's actually being played out behind the scenes here? Well, one thing that I do note is I have 1, 2, 3, 4, 5, 6, 7 squares, and maybe there's something going on with the order, the number of squares. Now, whenever I'm tiling again, I'm doing an imperfect tiling with an imperfect squaring of the rectangle. And what that would mean is one of the pieces has to be smaller than the other ones. Would you guys agree with that? If all the sizes are different, does that mean that one of the sizes has to be the smallest one? Yeah, it would have to be. Okay, so that's something I might want to really start considering now. I just kind of rushed into this and said, okay, well, if we just chopped it up, I actually want to take a step back and look a little closer at it. So if I have all my different squares, what would be a necessity in order to have this imperfect squaring of the rectangle? Well, once again, I got to have all the squares different sizes, and I got to have the smallest tile somewhere. I don't know. Suppose the tile was right here on the edge. Well, if the tile is right here on the edge, what would that force me to conclude? Well, I got to tile with something, so put my tiles up here. And what does that force me to have? That's going to force me to have another square fits right inside of there. And if it's going to be an imperfect squaring of the rectangle, folks, I can't have that. So what that illustrates is, if I'm going to have a chance of having this imperfect squaring of the rectangle, the smallest square cannot be on the edge. How about a corner then? Well, you can kind of go about the same scenario, put the square in the corner, and then take one of your tiles, put it next to it. But what does that force you to have? It's going to force you to have another square of the same size in order to fit in here, because for tessellation in this tiling, you can't have any overlaps and you can't have any gaps. Okay, so that would say then, if I have this case, if it does exist, what does that force me then to conclude? It can't be here. It can't be any of the corners. So it's got to be somewhere in the middle. Okay, now, we're kind of zero in on this a little bit. If it's right here in the middle, and and I put my squares up, I got a little problem. Because I have a little gap right there. But what if I took my square and I took it and I pushed it over? Well, that's a problem. But what if I took my square and I just pulled it down and pushed the other one over? That's not a problem anymore. So if I have a squaring of the rectangle, the smallest square, it's going to have this pinwheel shape to it. Later on, look at the tiles in the floor. If they're all different sizes of squares, you'll see something just like this. Okay, now a lot of times with those tilings, they're actually going to put some rectangles in it because it's a little complicated to actually do a bunch of squares everywhere. Take that saw out and just cut it, call it a day. Okay, so I got to have that configuration. If that configuration, if it's not there, it's just not going to work out. Okay, now once again, let's just kind of look at this. And let's say I have it actually in the center, and I'm really bad at drawing. I'm really sorry. I'm not sure I passed second grade, but these are squares. They look like rectangles. So let me go to the same scenario. Let's go ahead and label this. Okay, so we'll say y, x. I'll just go all the way around. And if this is y, this is x, has the dimension of x plus y, and x plus 2y, so on and so forth. And I'll do the same idea. I'll take the dimensions. I can take the length, the width. I'm just going to take something and go with it. And set up my system of equations, which really just one here in this case. I'll solve for x and y, find the relationship, and I see that we're going to get 0. So this whole entire thing will collapse down. There was no y. See, I thought that there was if I did this configuration. So what does that tell me then? If I'm going to do a squaring of a square, here I have 1, 2, 3, 4, 5. 5 squares is not enough. Because remember, the little one, the tiniest one, the smallest one's got to be in the middle somewhere. And we said, let's check this, see if it will work out. It doesn't work out. Okay, so 5 tiles are not enough. So I'm going to have some kind of tiling up here perhaps, or maybe down here. Let's analyze and see what might transpire. So I look at my configuration, and if I was to tile it like this, do you see the problem? This has dimension, let's say, I don't know, let's just say A. When we look at the tile 7, what dimension would it have? It's the square. It's also going to have a dimension A. And I can't have that. And likewise up there, 1 and 6 are going to have the same dimensions. So what I'm going to do is I'm going to have to take this and adjust this. I can take it and I can adjust it out so far. And then maybe I'll have a tiling down here. But that can also lead into some problems. So we'll take it and push it in. And likewise down here, I got to do something with the tile 7. That's going to cause some issues. And if I elongate it, this is going to maybe run into some issues as well. So let's take it and push it in. Okay. Okay, so here, it seems like, once again, 5's not enough. Maybe 9's the right thing. Maybe 9's the ticket here. Okay. Okay, so once again, what I'm going to do is I'm going to slice and dice. Instead of doing 7 regions, let's go ahead and just run through 9 different regions. And I'll go ahead and label again, D1, D2. And I'll do a similar analysis as I'm going around. Get all my dimensions. Set up my system equations by noting the fact that the dimension up here is the same as the dimension down here, as well as over here. Get my equations. It was fun making this, by the way. It took a really long time. Bang, there it is. There's your equation. Okay, so now I have a relationship that 2D1 equals 5D2, and what's this tell you about D2? Think about it from a number theory perspective. 2 doesn't divide 5 because 5's prime, 5's odd. It is kind of odd, by the way. 2 is prime, but it's also even. So it says that 2 has to divide D2. So I know D2 has to have an even dimension here, an even value. Okay. So I'll take this and I'll just drop it all in. Dot, 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 math magic. And there, that will work. And this delta, this can just be a free variable. I can call it 1, I can call it 2, I can call it 3, I can stretch it however I like. Okay, so here's my squared rectangle. Looks like I'm gonna have a 69 by 61, but eureka, we found something. Now, the question is, we do know that squared rectangles do exist, and we see a way of how we can construct them. That's kind of almost like blindsidedly going into it, though. I would like to have something a little bit more substantial. And just kind of a reference between what we did previously and what we did in the next case, a little bit of a difference here. This wasn't enough tiles. This is the right number of tiles for this to work out. Okay. So what's kind of this theory, or what can I say behind these perfect squared rectangles? Well, if I take a little bit closer look at it, at least for this one, to see what's really the underlying factor, the feature behind this, I can look at the dimensions again, look at the sides, and I see that this squares on top of this one, and also on the other one over here. And the thing to note here is I have these squares stacked on top of one another. And that talks a little about the length as you're adding up. Remember the Fibonacci spiral, 1 plus 1 is 2. 2 and 1 gives me 3. Now you can look at those blocks. Okay. So here's what I'm going to do. I'm going to take this configuration, and I'm going to look at all the horizontals and look at all the verticals. Now, for the horizontals, what I mean is, if I have a square that's touching right here, the line, I have squares right here touching that boundary, also right here, all the way down. And then I can also talk about these verticals, and the vertical lines. That's going to correspond to maybe this dimension going up and down. And I'm going to have each one for each one of these squares. Okay. So I'm going to take this and do a little bit of an isomorphism, just a great word to say. And I'm going to redesign it. I'm going to collapse it down into a bunch of wires. So what I'm going to do is I'm going to form a circuit. And the circuit, again, I take the horizontals and I create these horizontal lines. And for the rectangles, they all correspond to a vertical. So the horizontal line tells me a little about the correlations, how the squares are aligned together. So that information is being preserved when I do this. Okay, so that's kind of the insight here. Now, the next thing is, since I'm talking a little about correlations, I think there's a branch of mathematics that really talks about how things are correlated, how things are put together, and that's exactly what we do in graph theory. We look at dots, we look at how dots are connected, we look at the lines, we look at other things, but in graph theory we do connect a lot of dots. Okay, took a little while, but you guys got it. Bad joke, more coming, hang on. Okay, so here's the idea. All the horizontals, I want to take it and I want to collapse them all down to a single vertex, a single node. And if there is a vertical right here, what I want to do is I just want to connect them up to the vertex. Okay. Let's see. Sorry. Okay. So I'll take the first one, and I'll do that. And I'll take the next one, and I'll hit it. And then I'll do the next one, hit it. We just have a lot of fun with it. Okay, so I'm going to take my network, and I'm going to connect it up to something that's a little bit more accustomed to what we're seeing in terms of graphs. So here is the actual squaring of that rectangle recalibrated in graph theory. So I went from one branch of mathematics to another branch of mathematics, because this branch of mathematics was a little complicated, a little hard to understand, but when I took it to this higher branch of mathematics, I can start seeing things a little bit differently. And one of the things that I do see is I do have this electrical network. And if I have an electrical network, a flood of information starts rushing in as fast as possible. Now, one of the things I can start talking about now is conservations of the current. I can start talking about voltage differences. I can talk about Kirchhoff's laws. All these things are now into play into a really simple problem of Cheez-Its, tiling the floor, things you probably wouldn't have thought otherwise. So basically what it's saying is, if I put the current in, I'm not going to lose it. Well, don't worry about the resistance and the heat and everything. But if I put C1 in, it's going to get split up. Think of it like maybe like a waterworks system. You put a flow of water in. You can divert some of the flow this way, but some of the flow's got to maybe go the other way. So C1 over is equal to C2 plus C3. Also, here as I go around, the sum of the voltage around the closed network is going to be 0. And that's also going to be a little bit important here in a moment. So as I take V1 plus V2 plus V3 plus V4, I sum them all up, I get 0. Now, sometimes it's going to be reversed. And when it's reversed, maybe it's not going in the same direction. That's okay. We'll just take it and we'll look at the negative of it, and we'll reverse it, and we'll still get our 0 out of it. Okay. Now, do you guys kind of see what I'm doing? I'm establishing the framework to start establishing equations here. Okay, so Ohm's law, current, voltage, and resistance. I would talk about the resistance joke, but I might get some resistance from that. So we have our voltage and our current, and when I look at what's going in and what's going out, I can talk about the vertical and the horizontal measures, and that's how I want to look at this. Now, to make things a little bit more normalized, I'll go ahead and normalize it. So let the resistance just be 1 ohm. That would tell me that my voltage corresponds to my current. Okay, so that's going to be a pivotal part here in a moment. But first off, what I probably want to do is take this and hook up a battery and let the current fly through it. Okay, careful, it's been electrocuted, has energy through it. I warned you guys. Okay. So when I look at the network as current's flowing through it, one thing I notice here is I see a cycle. I see this cycle, and I color code this so you can see it a little bit easier. Look at the flow. It's all going down the same path. And right here, we're going to have a little bit of difference. Okay. Right here, going to have a little bit of difference here in a moment. How it's getting split up. Okay, here's another cycle right there. See how it comes in and gets split up. One goes this way, this one gets split up and it meets right there. And I have another one right here. As the current's flowing in, I have stuff right here flowing in, I got stuff right here flowing in. I have that cycle. Okay. So I see my different cycles. Let's go ahead and start labeling some of these, some different sides. V1, V2, remember voltage is the same as the current. So I have V1, V2, energy comes in, stuff's getting split up. So that tells me things like V2 is going to equal V4 plus V5. There's one equation. And V1 plus V3 It's going to get going to this node. It's going to get split up going this way and also going down this way. So it's a big old mess here. But for cycle 1, I can write it in terms of V1, V2, V3, V4. Because remember, let me go back a few slides here. Let's see, right here. I got the flow going all in one direction, but what do I do when it's going the other direction if it's not following this path? Okay, I can say negative V4, or I can kick it to the other side and say V1 plus V2 plus V3 equals V4. Okay. Okay, so let's get back to where we're at. Okay, so that's where these equations are coming from. Another one here, V4, V3, V5, right here. See V4, V6, it says V4, V6 come together. V5 is going the opposite way. So we can say negative V5, or we can just throw it to the other side. But the same thing here with cycle 3 that I see, and also cycle 4. Okay, so I can look at it from that vantage point. And when I have a system of equations, what does that naturally lead me to? A matrix. Okay, so I have a matrix here. Equation 1, equation 2, equation 3, equation 4, cycle 1, cycle 2, 3, and 4, and look at all my variables. Wow, that's a lot. Can I solve this system? Well, I'm going to have some free variables floating around. And, you know, I don't want that freedom. I want to be kind of locked down. I want to see what this actually is going to be, so I need some more equations. Okay, so let's go back to our system again, see if we can glean some more information. So when I look at it in terms of the current, V2 is going in, and what's coming out of it is V4, V5. So we got that conservation principle. So V2 is equal to V4 plus V5. And I can work my way around. Also, I can talk about coming in this way. I can also talk about coming in down this way and coming in over this way. Look, V4 gets split up to V3, V6. So that tells me the relationship here. Okay, just another one. Okay. See if I can highlight that again. It's a little hard to see. 5, 6, and 7 all come into 9. 1 and 3, 1 and 3 come in, and what comes out is 7 and 8. Okay. Okay, so I got 3 equations. Let's see if we can get one more. There it is. 4, and what comes out of 4 is 3 and 6. Okay. Okay, so I got my other equations. I can also now throw them into the mix. I can talk about a matrix. But I'm talking about the same variables, V1, V2. I can talk about the current, I can talk about the resistance, the voltage. Let's make a big old matrix out of it. And if you notice, I'm going to augment it here. So what's the next step that I would do once I have my matrix? Now, notice what we did. We took a tiling problem, we took it to an electrical engineering problem, took it our graph theory, electrical engineering, and then we threw it right back into a matrix. Just one branch right after another, isn't it? And if I want to solve this, what would I do? Hopefully you know what to do so you can pass the class, I guess. REF it. You have to do some row operations. So what you have to do is you're going to have to take this matrix and transform it into echelon form. Let's transform it. Let's do that again. Let's transform it. Okay. And here, I have a bunch of basic variables. I have one free variable. So I can put this into parametric vector form. V9 is a free parameter. Okay, so I can look at my vector, solve my system, take everything, plug it all in, and this is what we have. Now, because V9 is a free variable, I can make it whatever I want it to be. And if I want to look at integer values, which I do want to look at integer values, I can make it a multiple of 28. So I just make it 28, and then I get all the other configurations I need for all my squares. Okay. So let me just kind of back up a little bit so you can see it a little easier. Okay, so V1, 36. V2, 25. Remember what these vertical lines mean again? It represented the square. And remember what the vertex meant? It's the correlation between the squares, how if you have a line connected to the vertex, that means there's going to be a square on the same horizontal. It's going to be at the same level. Okay. V3, 9, 16, 2, 7, 5, 33, and 28. We'll take this and we'll transform it back. And there it is. Okay. So we can look at electrical networks in order to figure this out. And let's just go back real fast. Whoops, sorry. I gotta hit the magic button. Okay, so we got 36, we have 25, that's your 61 again, and then you got your 69 right there. Okay. So we're still talking about these rectangles. Now, to do the squares, we can go through kind of a similar analysis, take it a little bit more in detail, a little more in depth, and there it is. Okay. You're going to need a little bit more in order to do it, but we kind of have an idea of how we can set this up now. We can use linear algebra, a little bit of graph theory, and we got our problem. Okay, good. 112. Now, later on, see what you can do with all this. See if you can actually find your own perfect squaring of the square or of a rectangle. The order need not be unique, and actually there's some stuff you can look online. There's some diagrams. A lot of research has been done on this over the years. But we'll just kind of leave it right there and see if you guys have a question.
Questions for the speaker? Is that the smallest known perfect squared square?
I think it is.
That's the smallest you can go?
I think 9 is.
No, I mean the 112 by...
Oh, that one? No, I think you can go a little smaller than that.
You can go smaller than that.
You can go smaller than that.
But that does settle the conjecture you showed earlier that in 1930-ish, that can a square be perfect squared?
Yeah, it does settle that, because here it is.
And that was, what year did that happen?
Oh, let's see. I think that was, when it was found, I think it was 40. I think it was 40.
Okay.
And kind of the interesting thing behind that is when they're trying to figure out the squared rectangle and the idea, trying to understand the theory behind it, they had a bunch of squares they cut out and they put it on their desk, and their mom came in and she cleaned things up. After they spent all this time and they got their perfect square in the rectangle, their mom took the squares and she rearranged it into another perfect square in the rectangle. And they're like, first they're a little upset, and they're like, oh, Mom, you found another one. And that tells us then it's not unique.
Okay.
So that does bring up a combinatorial problem now. How many are there if you have 9 or 10 or 11, using the order, the number of squares within it. So moms can be great. I mean, there's no doubt behind that. Good.
I don't want to hog the questions, but I do have another one. On your electrical network diagram, how did you decide on the direction? I noticed it was directed. How do you decide on the direction?
Just kind of make a choice and go with it, because you can take it and you can do it this way. But what's the difference between this squaring and this squaring?
I mean, the edges of the network, how do you determine the flow, whether they're, what direction they point?
So you mean, why not put it in this way as opposed to this way?
I think we would do the calculation.
Your
if they're less
vertical
negative.
coming down, how do you know if they're coming down or going up?
Just kind of put an orientation on it.
Just give it an orientation?
Just give it an orientation and just go with it.
And that determines equations that you need
Yeah.
to solve?
Right.
Okay.
You could, I mean, you could reconfigure it all and tip it over and do something similar, or you
Okay.
can go from the bottom.
Any other questions for the speaker? Sorry, I hopped the time there for a little bit. Yes?
I don't know if you're able to get to the slide where you have the arrows pointing all the different directions.
I might be able to do
This
that.
question. But when you did the calculations, if you had an arrow going the other direction, would it just make the calculation come out as a negative, showing that you, I guess, picked the wrong direction?
Yeah, let's see. I just have 9 slides here, Wesley. Let's see if we can find it. You're talking about this right here?
One more. Or when you get to the big picture and you add arrows on it, yeah, there's your arrows, they popped up. You just put those.
Okay, so if flow's coming in, you electrocute this, put energy into it. It can't go reverse.
I got it.
I see what you're saying now.
I see.
Yeah.
Okay.
If you guys want to, think about like a pipe system, waterworks. You throw some water in, it's got to go with the flow. It's got to go in a certain direction. You're not going to have that backward flow. Hopefully you won't have that backward flow.
Okay.
Bad when it happens.
Okay. All right.
Was that your question, Wesley? Or
I think that's it.
okay. Yeah, Chase, what you got?
So the blue shape there is it's essentially the same information as the actual square, right? You say they're the same?
The
essential information.
the length of the square is going to correspond to the current. And what I'm doing is I'm using Kirchhoff's laws to understand how things are correlated all together, because when I start making these tilings, they're correlated together. One way or another, I'm trying to understand how things are being correlated. And it's really hard to just kind of say, I'm going to put a piece here and put a piece here and kind of blindly go into it. But if I have a little bit of an extra push in the right direction, using these Kirchhoff's laws and these circuits, then I can set up a system of equations, and I can say, will it exist or it won't exist? I don't have to keep trying the different numbers and see if it's just going to fit right.
Time for one more question?
Yep.
This is all two-dimensional. Is there a three-dimensional for this?
Oh, Jason, that's a great question. Yeah, there's some stuff out there. I think that's probably an open question, actually.
Perfect cube of a cube?
Yeah, I think that is. But I can definitely get like 4 different cubes, put them together, and I can start making some, but they're the same size. Yeah. So work on that problem and let me know about it. Maybe we'll talk about some bonus points or something.
All right. I think we're out of time. Let's thank our speaker. See you next week. Dr. Thompson is going to talk to us about Calculus 3 and statistics. Okay. Hey, Jimmy, you want to kill that recording? Okay. Good seeing you.